In this final video covering the material in Chapter 3, we're going to talk about numerical summaries of the relationship between two variables. As we go through this discussion, I would like you to keep in mind our graphical summaries of the relationships between two variables, in particular scatter plots. We're going to talk about two measures of association between two separate variables, the covariance and the correlation. These will be very closely related to the line of best fit that we put through a scatter diagram and our interpretation of the relationship between the two variables in a scatter diagram as being either a positive relationship with an upward sloping trend line, an inverse relationship with a downward sloping trend line, or no relationship at all with a flat trend line. Covariance first. Covariance is a measure of the linear association between two variables. Positive values indicate that the relationship between the two variables is positive. In other words, higher values of one variable are related with higher values of the other variable. Negative values indicate an inverse relationship or a negative relationship, such that higher values of one variable are associated with smaller values of the other variable. Here are formulas for computing the covariance, and just like with our other measures, we have a sample formula and we have one that is applicable to the population parameter. So once again, a sample point estimate and a population parameter formula. We denote the covariance between two variables x and y in a sample as x subscript xy. We denote the covariance in the population between two variables x and y as sigma subscript xy. In calculating the sample covariance, for each observation and moving observation by observation, we take the difference between each x value and its mean, and we multiply it by the difference between each y value and its mean. This looks very similar to the formula for the variance that we've already covered, except there we were taking the difference between each value of variable and its mean and squaring it. Now, rather than squaring it, we're taking it and we're multiplying it by the corresponding value of y and its mean. We take the product of these two deviations from the means for every single observation in the data set, and we add them together after we have multiplied the two deviations together. We then take, in some sense, an average of those deviations from the mean by dividing by n minus 1. So this is really a measure of the average association of how x varies from its mean when y varies from its mean over the sample data. If consistently, when x is greater than its mean, y tends to be greater than its mean, then the sum of the products of x and y are going to be positive, and we're going to divide that by n minus 1 and get a large positive number. If as x tends to vary above its mean, y tends to vary below its mean, then the product will be negative. We'll add up a large number of large negative values, and when we divide by n minus 1, we'll get a large negative value, and the covariance will be negative. When we move from the sample formula to the population formula, the only differences, which you should come to expect by now, are that we replace x bar with mu sub x, and y bar with mu sub y. So mu continues to stand for the population parameter of the mean. To identify the difference between the variable x and its mean in the population and the variable y and its mean in the population, we add the subscripts x and y. Once we have calculated the deviation of every value in the population from its mean for both x and y and found the products, we add all of those values together and we divide by capital M, which we know stands for the number that's in the number of individuals or observations that are in the entire population. The correlation coefficient is a measure of linear association, but not necessarily causation. There's a famous quip in statistics that correlation does not imply causation. Just because two variables are highly correlated, it does not mean that one variable is the cause of the other variable. It simply means that when one variable moves in a particular direction, there's a strong tendency for the other variable to move in a particular direction. Here are measures of the correlation coefficient, and they are based on the calculation of the covariance. Here we have, for samples, we have a formula SXY, which is the covariance that we calculated 2 slides ago, and we essentially normalize that by dividing by the standard deviation of x times the standard deviation of y in the data. For populations, again, there's a corresponding population parameter. The correlation is typically denoted with rho, subscript xy, to denote the two variables for which we are calculating the relationship between. We take the population measure of the covariance that we calculated previously, and we divide it by the standard deviation of x multiplied by the standard deviation of y. The nice thing about the sample correlation coefficient and the population correlation coefficient is that they are bounded between -1 and 1, with -1 being a perfect inverse relationship between the two variables and +1 being a perfect positive relationship between the two variables. These measures therefore are independent of the units of measure that we choose when we measure the data x and y. These measures will also be very closely related, as is the covariance, to the slope of the line of best fit in a regression analysis, which we will cover later. The coefficient, again, can take on values between -1 and +1. Again, values near -1 indicate a strong negative linear relationship, and values near +1 indicate a strong positive linear relationship. That is, in the case of a correlation coefficient near -1, we would have a downward sloping trend line through a scatter plot. And if we had a value of the correlation coefficient that was positive, and as it approached +1, we would see a strong relationship with a positive upward sloping trend line and a scatter plot between the two variables. The closer the correlation is to 0, the weaker the linear relationship is between the two variables. Here's a simple example. We have some data from a golfer who's interested in looking at the relationship between their driving distance and their 18-hole score. This golfer has gone to the golf course and he's played 6 different rounds of golf, and he's calculated his average driving distance and his score. We're going to calculate the covariance and the correlation between this golfer's score and his driving distance. Recall that lower scores in golf are preferred to higher scores in golf. In calculating our covariance, we're going to take each value of x and we're going to subtract the mean from it. So we need to find the average of our x values, our average driving distance. And in this data set, the average driving distance across the 6 rounds is 267. We also need the average score. The average score for this golfer is 70. So for each value of x in the data set, we are going to subtract 267. That is going to result in the third column in the table. For example, the value of 10.65 is equal to 277.6 minus the mean of 267. Doing that for every single value in the data set, all 6 rounds of golf, we have the following column of data. We do exactly the same thing for our y variable, our score. we're going to take the first value of 69 and subtract from it the value of 70, which is the average score. Clearly, if we take 69 and we subtract 70, we get a -1. If we take 71 and we subtract 70, we get 1. We do this for every value of y in the data set, all 6 rounds of golf, and we come up with the following column of data. This last column of data takes the 2 columns immediately to its left and finds the product of them. In other words, 10.65 multiplied by -1 is equal to minus 10.65. Minus 7.45 times 1 is minus 7.45, etc. We then add up all of these values in the last column, minus 35.4. The standard deviation is then the minus 35.4 divided by the appropriate degrees of freedom, which is equal to 69. Here are the final calculations. I'm sorry, and I misspoke on the previous slide, which is why I paused momentarily. The degrees of freedom, I was going back to our other example with a sample size of 70. That's incorrect. Here, obviously, we moved to a different example with golf rounds. There are 6 golf rounds. 6 minus 1 is 5, so we're going to divide by 5. So I misspoke on the previous slide. Regardless, we take our minus 35.4, and we divide by 5, and we get our sample covariance of minus 7.08. The negative sign seems to suggest that if we have a longer driving distance, we're going to lower our score or improve our score on the golf course. Here's the sample correlation coefficient. The minus 7.08 is somewhat difficult to interpret. Is that a strong relationship between driving distance and score, or is it a weak relationship? It's easier to tell if we take the sample covariance and we translate it into a correlation. Taking the value of minus 7.08 and putting into the formula for the correlation, we will take it and divide it by 8.21 and 0.8944. These were the standard deviations of driving distance and score, respectively. Plugging these into the formula here, all of the values for the correlation coefficient shows a very strong relationship between driving distance and golf score. Minus 0.96 is very close to -1. That's a very, very strong relationship between driving distance and an improved golf score or a lower golf score. Here's a scatter plot just to bring this back to some of the material that we covered in the previous chapter. What I have plotted is driving distance on the horizontal axis, and I've plotted golf score on the vertical axis. I have done a scatter plot, so each one of these points represents a different game of golf from our data set. And you can count them up and see that there are indeed 6 different rounds of golf. The downward sloping dotted line is a line of best fit, which we will have a lot more to talk about later. But you can see that the negative correlation and the negative covariance is indeed associated with a downward sloping trend line. The only other thing I would point out at this point is that the trend line passes through the average score and the average driving distance in the data set.